Okay, so when we do most unit conversions, we're going to be multiplying by a fraction. There is one exception, and that's where we're converting between different temperature scales. And when we're doing that, we're actually going to use formulas depending on what temperature scales we're converting between. And the reason for this is because the different temperature scales have different 0 points. So for example, 0 Kelvin is the same as minus 273 degrees Celsius, and 0 degrees Celsius is the same as 273.15 Kelvin. So the 0 scales are offset by 273.15 units. Now it gets even more complicated because 0 degrees Celsius is the same as 32 degrees Fahrenheit. So you can see all three of the common temperature scales that we're going to be using have different 0 points. So what that means is when we're converting between different temperatures or different temperature units, then we need to use formulas that take into account the difference in the 0 point. So this question is all about converting between Celsius and Kelvins, and the relationship is this, that the temperature in degrees Celsius is equal to the temperature in Kelvin minus 273.15, or alternatively we can say that the temperature in Kelvin is equal to the temperature in degrees Celsius plus 273.15. So we're going to be using this first formula here, aren't we? Because we're going to be converting from Kelvin into degrees Celsius. So what we need to do in each case is to take the temperature that is given and subtract 273.15 from it. So let's give that a go. So in the first case, what do we need to do? Take our temperature in Kelvin, 210, and then we're going to subtract from it 273.15. And there we go, it's negative 63.15. Now it gives a little bit of advice. It says round your answer to the nearest degree. So we're going to record this just as negative 63 degrees Celsius. So for the next one, same deal, 159 Kelvin minus 273.15. There we are, minus 114 to the nearest whole degree. So minus 114 degrees Celsius. And then finally, 319 Kelvin, 319 minus 273.15. And there we go. And that is 45.85. So to the nearest degree, that would be 46 degrees Celsius. So we never round down, but we may round up if need be. We'll talk a little more about rounding later on. Okay. So this one, again, it says interconverting temperatures in Celsius and Kelvin. So remember, degrees Celsius is equal to Kelvin minus 273.15, or we can go the other way. Kelvin is degrees Celsius plus 273.15. So what have we got to do here? It says an organic chemist measures the temperature of a solution in a reaction flask. Here is the result. T equals 88.4 degrees Celsius. It says convert temperature to SI units. Now the SI unit for temperature is the Kelvin. So what that means is where they're just asking you to convert it to Kelvin, and then it says be certain that your answer has the correct number of significant figures. And we'll talk about that in a moment. The first thing to recognize here is that we're going into Kelvin, so we've got to add 273 to it. So let's just get the calculator answer. So Kelvin is going to be 88.4 plus 273.15. So if I put that into my calculator, 88.4 plus 273.15. There we go. 361.55 Kelvin. Now here's the thing. When we add numbers together, then we always go to the number of decimal places of the number that has the smallest number of digits after the decimal point. So you can see that this number was given to plus or minus 0.1, whereas this one goes all the way out to the 0.01 place. But when we add them together, we can only be as good as our worst measurement. So we can only go out to the 0.1s. So what that means is we're going to cut off there. So then we have to ask, do we leave our number alone, or do we round up? And because this is 5 or higher, the first digit that is being dropped, that means we're going to round up. Okay, so we're going to round this one up to 361.6 Kelvin. And like I said, we go out to the 0.1s because that is the measurement that we were given was in the 0.1s, and that is the least precise of those two measurements. A little bit complicated, that one, with the rounding and the getting the correct number of significant digits. But the important thing is that our precision is limited by our worst number. So we have two rules when it comes time to deciding significant figures. The first rule is for adding or subtracting, and it says you always go with the greatest uncertainty. So in this case, our first number had uncertainty in the 0.1 positions, and our second number had its uncertainty in the 0.01 position, so we went with 0.1. Now, when you're multiplying or dividing, you always go with the least number of significant figures. So you want to be a little bit careful there, because this first number has 3 significant figures, 1, 2, 3. The second number has 5 significant figures. So if you'd accidentally used the wrong rule, you would have said that we should go with the least number of significant figures, and you would have rounded this off at the 1 point there, at the 3 significant figures there, and that would have been incorrect because we needed to round at 0.1. So for adding or subtracting, you always go with the greatest uncertainty. For multiplying or dividing, you always go with the least sig figs. We'll talk a lot about that as we go through this class. Okay, so it says the average temperature at the South Pole in November is 29.1 degrees Celsius. Convert this temperature to degrees Fahrenheit. So when you're converting between degrees Celsius and degrees Fahrenheit, you've got two problems. 0 degrees Celsius is equal to 32 degrees Fahrenheit. 100 degrees Celsius is equal to 212 degrees Fahrenheit. So what that means is, in the space that you have 100 degrees Celsius, you have 180 degrees Fahrenheit. So 180 Fahrenheit units is equivalent to 100 Celsius units. So not only are the 0 points different for these two scales, the size of a Fahrenheit unit is also different from a Celsius unit. So it's kind of a little bit complex. So how do we convert? Well, we have to keep in mind that we have to make account for both of these things. So the little formula that we have is degrees Fahrenheit is equal to degrees Celsius times 9 on 5, and that takes into account that we get 180 Fahrenheit units for every 100 Celsius units, and then we have to add 32 to account for the difference in the 0 points. So we have to do two things, right? So here we go, degrees Fahrenheit equals degrees Celsius, which was minus 29.1, times 9 on 5 plus 32. And let's see what we get. Minus 29.1 times 9 on 5 plus 32. There we go. There's our calculator answer, minus 20.38. Okay, degrees Fahrenheit. Now let's think about our units here. It says be sure your answer has the correct number of significant figures. So the important thing to recognize here is that the original data was given to 0.1. The 9/5 here is what we call an exact number, and so is the 32. It is also an exact number. So what that means is we're going to give our degrees Fahrenheit to the 0.1 position. So it's going to be minus 20.1 degrees, 0.1, minus 20.4 degrees Fahrenheit, because we're going to round there, and 8 is bigger than 5, so we're going to go up by 1 in that last digit. Okay, moving on. Now, in this problem, what we are going to have to do is name different components of the scientific method. So it's not too bad. There are 3 written descriptions of different activities, and we have to decide what the missing word or short phrase is. Now it does say missing words, so, and then it has just singular here. So I want to think, it's only going to be the one word. So starting from the beginning of the scientific method, what we're going to do is we're going to do experiments, which is a well-designed / controlled procedure to collect data about our system. So that's an experiment. We may also make observations, which is just simply it's data about our system. So observations might come from an experiment, but they can also just come from looking at nature. Now, once you've got a bunch of experimental results, you can summarize them in what's called a scientific law, and that's a summary of the results from many experiments / observations. Then you might come up with what we call a hypothesis, which is a tentative explanation that is testable for, didn't really tentative. Sometimes it's really hard writing on this glass, and sometimes things don't appear, or they appear in a weird way. A tentative explanation that is testable for a set of data. So you got a bunch of data, and you can you can kind of recognize a hypothesis, because it kind of tells you, it tends to have things like because, right? Because it's explaining, right? It's actually giving a reason for why things are happening. And then finally, we have a theory, and this is a well-tested and accepted explanation. For data on a system. So this is like, more than one person has come up with this. And the thing about a theory is that it has the property of being able to make predictions about related systems. Can be used to make predictions about related systems. So keeping that in mind, we've got 1, 2, 3, 4, 5 terms there. Let's see what ones best fit in here. So here it says, after studying the position of the planets in the night sky for some years. So he's collecting a bunch of data, right? So it's not a single experiment, it's not a single observation, it's a bunch of data. So that means that it's not going to be experiment or observation. John discovers a something which he expresses as an equation that can be used to predict the location of each planet every night. And this has got to be a law. It doesn't tell you why, it just tells you what. And it's not just based on one observation or experiment, it's a bunch of experiments, right? A bunch of observations. There they are for years, right? So yeah, that's it. It's a law. It's a summary of a whole bunch of observations. All right, let's move on. Galileo decides to test the hypothesis that all objects should accelerate at the same rate under gravity. So he conducts a something. Well, there's really only one thing it can be, and it's got to be an experiment. Right? Because theories, hypotheses, laws, and observations are not conducted. They can't be conducted. They are, observed, and they are, proposed and things like that, but they're not conducted. Okay, so then it describes his experiment. He takes 2 balls, one heavy and one light, and drops them from the top of a tall tower, measuring the time it takes them both to hit the ground. He does this 10 to 12 times and averages the results. And clearly it's a well-designed, controlled procedure to collect data, right? So it meets the criteria of experiment. Okay, Tycho, so he's a Tycho Brahe, he's an astronomer. Looking through his telescope one freezing winter night, makes a something. The planet Mars is exactly 0.29 degrees higher and to the right of where it appeared at the same time last night. So this is just a single thing that he did, right? And what is he doing? He's collecting some data about the system. This is an observation. An observation, all right? He's just looking and he's just observing something, and he wrote down what he observed. Okay, not too bad. Okay. Distinguishing mixtures from pure substances through physical properties. So we have to think about this. distinguishing mixtures from pure substances. So mixtures have the characteristic that they can have multiple physical properties. Right? So if I have a mixture of sand and sugar, the sugar has a lower melting point than the sand, and the sand has a high melting point. So I have two different melting points present, right? And if I was to heat up a mixture of this this mixture of sand and sugar, the sugar would melt first, and then later on the sand would melt. So that would be an example. It could be the density. If I have a mixture of oil and water, there are multiple properties and physical properties. The oil is less dense than the water and will float on top of the water. So in mixtures, we're going to have multiple physical properties present. In pure substances, we have only one value for each physical property. All right? So if I have a pure sample of sugar, then it will dissolve in water, right? There's one solubility in water. But if I have a mixture of sand and sugar and I add water to it, the sugar will dissolve and the sand will stay behind. I have two properties for the solubility in water, two values for the probability for the solubility in water. So let's have a look at this. It says sample A is a solid yellow cube with a total mass of 50 grams. Okay, that doesn't help. The cube is put into a beaker filled with 250 mils of water. So this is something about solubility, isn't it, right? Does it dissolve in water? The cube collapses into a small pile of orange powder at the bottom of the beaker. When this powder is filtered out, dried, and weighed, it has a total mass of 29.9 grams. Okay, so you take 50 grams and you put it into water, and 29.9 grams dissolves. And so then that must mean that you have 20.1 grams. Sorry. 29.9 grams doesn't dissolve. That's the stuff that doesn't dissolve. And 20.1 grams dissolves. Okay. So that's when you dissolve it in 250 mils of water. And then you're going to do it again. And you do it again, but this time you use twice as much water. All right, so that's with 250 mils. Okay, so now you do it again. You take 50 grams. And you do it this time with 500 mils. And what happens? Sure enough, 30 grams doesn't dissolve, so basically the same as what you got before, and 20 gram does dissolve. Okay, so you basically got the same result. So the question is this a mixture of two things where you got 20 grams of something that is soluble in water and 30 grams of something that's not soluble in water? Or alternatively, is it just that in the first case, you just didn't add enough water, and if you added more water, then it all would have dissolved? Now, the fact that you get exactly the same result, regardless of whether you use 250 mils of water or 500 mils of water, indicates that what you've actually got is a mixture where you've got 20 grams of something that is soluble in water and 30 grams of something that's not soluble in water. And the reason that I know that is because if it was just the fact that I didn't add enough water, when I added more water, more of the stuff should have dissolved. So this has to be a mixture for sample A. Sample A has to be a mixture, because if I added more water and it was a pure substance, more should have dissolved, and it didn't. All right, so that's kind of that's what's going on there. All right, so we've got two things, and they have different solubilities in water. 20 grams of it doesn't dissolve, doesn't matter how much water you add. 30 grams of it can dissolve as long as you have 250 mils or more. All right, so now we've got sample B. It says it's a grey powder and it doesn't smell good, okay? 15 grams are dissolved in ethanol, okay? So that's fine. So it all dissolves into ethanol. So it all has solubility in ethanol. 0.5 milligrams of the resulting black solution is carefully dropped onto a thick sheet of paper laid in a tray. Okay, so what this is getting at is the idea of something dispersing through another substance. In this case, it's dispersing through paper. And now sometimes when you drop a liquid onto paper, what will happen is you leave it for a little while and it'll spread out into rings with different colors. And the reason being is that it's because it's made of multiple substances that interact with the paper to different extents. And we actually can use this in chemistry to separate out different things from a mixture. So it's called paper chromatography. So what happened here is, so what we'd be looking for if this was a mixture would be like multiple rings that this thing separates out into, indicating different substances that interact with the paper to different degrees. Now what happened here, it says after 30 minutes, the initial round black stain has spread out and faded in color to a deep purple. So what happened here was we didn't get multiple things, our sort of like our little blotch of stuff, it just got bigger, right? It just got to be like a bigger blob that was a slightly lighter color. So it didn't do the whole separating out into multiple things. So the truth is we can't really tell here. Now, this idea of things moving through paper or through any kind of medium at different rates is kind of interesting. So, for example, if you have a field of, I'm going to try and draw these. This is a field of flowers, right? There you go. A field of flowers. It doesn't have very many flowers in this field of flowers. There's the ground. It only has about 3. And these flowers are pretty miserable looking. There we go. Now, we all know if we were to release, say, like some bees, we can tell these are bees, right? Because they've got a stinger on the end. See, there's his stinger. The bee would come along and he would move through the field pretty slowly because he's going to stop at every flower and collect pollen, right? Yeah? Now, if I was to take, say, another kind of bug that doesn't care about collecting pollen, let's say I took a fly, and you can tell there's a fly because he's got big bulgy eyes and he doesn't have stripes or a stinger, then the fly would go straight through, right? So the fly would come through first and the bee would be like kind of, still back here because he's collecting the pollen from the flowers. So I could use a field of flowers to separate bees from flies. Does that make sense, right? Now, when I drop a solution of a mixture on paper, the same thing can happen, that the components in that mixture interact with the paper to different degrees, and so they will spread out just like the bees and the flies, okay? And now we use this in chemistry, quite a bit. So it's called, like I said, paper chromatography. There we go. And I'll show you some images so you can see it. And this is the classic one where you have Here we go. What we've got here is you take a little bit of mashed up leaves, and then you dip it into some liquid, and the liquid rises up the paper, and all of the different colored compounds that are present in plants will separate out according to how they interact with the paper. And so carotene, which is the compound that makes carrots orange, doesn't interact with paper very strongly at all, and it'll move through the paper really quickly, right? And then chlorophylls, and they come in different kind of types, they interact with the paper quite strongly, and so they barely move as the solvent moves up the paper. So that's a good example of how we use this different mobility through paper. All right. Now, this one's about distinguishing physical and chemical properties. So, physical properties are things that you can measure without attempting to rearrange how the atoms are connected. So, we got no attempt to reorganize connections between atoms. So a classic like physical property would be like measuring the temperature of something, right? Or it could be measuring the density of something. That would be a classic physical property. Chemical properties are what happens when we attempt to reorganize connections between atoms. So a good example could be setting fire to something. Well, attempting to set fire to something. So you're going to try and burn it, right? Flammability. And we'd either say that it is flammable or it's not flammable. That would be an example of a chemical property. We could test whether something is reactive with oxygen, right? See what happens when we leave it out in the air. Does it rust? Does it corrode? And we say it's either easily corroded or it's not corroded. Something like that, right? That would be an example. So let's have a look at these descriptions, and we have to decide. So it says, a sample of X is carefully weighed and put inside a sealed calorimeter. That doesn't really matter what a calorimeter is. It's just a device that we're going to seal this thing inside of. Pure oxygen gas is injected into the calorimeter and the mixture is ignited. Oh, we're trying to burn it. In fact, we are burning it because it says that we ignited it. After all of the X has reacted with the oxygen gas, the temperature rise of the calorimeter is measured, and from this change in temperature, the value of C may be calculated. So C is a measure of how much energy is being released in this chemical reaction between our substance X and oxygen. So this is most definitely a chemical property. We're talking about how much energy is released when we react it with something else, right? So we're not even like attempting to react it, we are reacting it, okay? So the next one is about this property M. A small sample of X is put on the pan of a sensitive balance. Now in chemistry, a balance is just a fancy way of saying a scale. And its weight measured. Next, a magnet is brought near the pan and the weight is measured again. From the difference of weights in and out of the magnetic field, a value of M may be calculated. So this is pretty cool, right? You got a scale, there it is, and then you put an object on it, and then you hold a magnet near it, right? And you measure the weight again. So clearly, if it's attracted to the magnet, it's going to weigh less. If it's repelled by the magnet, it's going to weigh more, right? So that makes sense, doesn't it? And if it was attracted enough, it would end up like you would call 0 for the mass. All right, so are we attempting to reorganize how the atoms in X are organized, are connected to one another? And the answer is no. We're just measuring how X interacts with a magnet. So this is a physical property, right? This is a physical property. Magnetism is a physical property. Now it says a sample of X is melted, okay, and put into a reservoir from which a very thin tube leads down. So we're going to pour it into a container, and it's going to flow down as a liquid, and it's going to flow down a really thin tube. The rate at which X flows out of the tube is measured. And from this rate, the value of V may be calculated. So what we're doing is this. We basically have got a funnel that has a really thin tube at the end. And then we're going to pour the liquid in here, and we're going to see how quickly it flows out. So if you had something like water, it would flow out very quickly. But if you had something like honey, it would flow out slowly, right? And so that's the property that we're looking at, is how easily does it flow through the thin tube. Now, to do that, no atoms are being reorganized in how they're connected to one another, right? We're just looking at how runny this stuff is. So again, this is a physical property. And this property is the viscosity, how easily something flows. Now, it's actually interesting because there's an experiment that's at the University of Queensland in Australia. It's called the pitch drop experiment, and it is the world's longest running scientific experiment. And what they have is a really, really thick and extremely viscous liquid called pitch sitting in a funnel just like this. And it takes a very long time for this to flow through. In fact, there haven't been very many drops at all that have come through. And let me have a look. Here's the timeline. It takes around, and it looks like it's slowing down, it takes around like 8 to 13 years for one of these drops to fall, right? And this has been going since 1927. There you go. So they've been running this experiment for quite some time. And I think it says, it just says that it's a long-term experiment. But I thought that it was the world's longest experiment. But maybe it's not the world's longest experiment. Anyway, but here it is here. So this is exactly what we're doing, right, in this experiment. And they're measuring this thing called viscosity, like how easily it flows. Okay, cool. All right, let's move on. This is about distinguishing extensive and intensive properties. So, what is an extensive property? An extensive property depends on amount. So the classic one would be would be mass. Right? The more you have, the bigger the mass, right? That's a classic extensive property. An intensive property doesn't depend on amount. So a classic example is temperature. Right? Because if I have a cup of boiling water and I pour half of it out, I've just got half a cup of boiling water. The temperature will be the same, right? Okay, so that's a classic intensive property. So let's have a look here at this question here. This looks like it's going to be the properties of pizza. Pizza. Second Avenue Pizza sells pizzas in various sizes, okay? decide whether each property of their pizza listed in the table below is extensive or intensive if you can. So this is about properties of their pizzas. So it's all about pizzas. Okay. Does the property depend on the amount of pizza? Okay. Does it depend on the amount of pizza? So let's have a look. The amount of dough it takes to make the pizza. So if you have a bigger pizza, does it take more dough? Yes. If you have a smaller pizza, does it take less dough? Yes. So that means that it must be an extensive property. The thickness of the crust. If I have a big thin crust pizza, the thickness of the crust would be the same as if I have a small thin crust pizza. That is an intensive property. It doesn't vary with the size of the pizza. So that is intensive. And then it says the amount of cheese topping per square centimeter. Now this is important. If you just had the amount of cheese topping, then that would be extensive, right? Because we'd be looking at, two different size pizzas. Clearly this guy has more pizza on it. But it says per square centimeter. So we've got a square centimeter there and we've got a square centimeter there. It doesn't matter. It's just 1 square centimeter of a big pizza or 1 square centimeter of a small pizza. It's not going to make any difference. So that is an intensive property. Now this is a good point. In general, when it's like per amount, it's intensive. Okay? If you see that, always be thinking that it's probably going to be intensive. Okay, distinguishing elements from compounds. So elements, 1 atom type present. Compounds, at least 2 atom types present. Okay. So let's see what we've got here. Well, in substance A, we've got these green atoms and we've got these yellow atoms, so it has to be a compound because we've got 2 atom types present. In substance B, we've got these single molecules here that have 2 types of atoms. There's these white atoms, and then there's the larger green ones. So it's got to be compound. In C, again, 2 types of atoms are present in each of the molecules, so it has to be compound. But in D, we only have 1 type of atom present. It's those red ones. It's got to be an element. So that's it. Pretty straightforward. Okay. Now this looks more complex. Distinguishing compounds and mixtures. So compounds are examples of pure substances. The other kind of pure substance is an element. There is only 1 kind of molecule in a pure substance. They have 1 kind of molecule, but those molecules have at least 2 atom types. Okay. Now, mixtures have more than 1 pure substance present. And remember, pure substances are of 2 types. They're either compounds or elements. So if you have greater than or more than 1 type of pure substance present, then we know it's a mixture. And remember, like I said, pure substances, always tricky writing on this glass. Pure substances are either compounds or elements. So let's see what we've got here. Decide whether each sketch shows a sample of an element, a compound, or a mixture. So the first thing for X is that there are two types of atoms present, so it cannot be an element. The second thing is that there are two different types of molecules present. There are the ones that have those like bluish molecules and the ones that have the reddish ones. So it cannot be a compound. It has to be a mixture. And it is a mixture. It's a mixture of two different elements. The one that's got these diatomic red molecules and the one that's got these diatomic blue molecules. Now if I look at substance Y, I can see that there is only one type of molecule present. So it is not a mixture. And I can also see that there's only one type of atom present. So it is not a compound and it has to be an element. There we go. Now Z, I want to look at real close. When I look here, I can see that there is only one type of molecule present. It's the molecule that has two of the blue, and then it's also got two of the red. And the blues are kind of on the end, and the reds are in the middle. So every molecule sort of looks like that. So the fact that I only have one type of molecule present tells me that it's not a mixture. And then the second thing is that I've got two different types of atoms there, so it can't be an element. It's got to be a compound. All right, on to the last one. Now, looking closely, because I don't want to miss anything, I see that there is only one type of molecule. They all look like this. We've got these two blue ones on the end with a red one in the middle. And every molecule is like that. So because there's only one kind of molecule there, it can't be a mixture. It can't be an element because we've got two different types of atoms present. So that means that it's a compound. Okay, so we've just got to kind of work through that slowly. All right, we're getting near the end. We've only got 3 left. So it says classifying substances from a sketch. Okay, we need to look at this closely. It says classify the substance shown in the sketch below. You can click the other tabs in the sketch to get a magnified view. And we've got 1,000 times, and then we've got 10 million times. And then it says, be sure to check all the boxes, which is really telling you that there could be more than one, on the right-hand side that are correct for this substance. Okay, so just looking at the normal view, what can we decide about it? Is it a gas? Well, it's not a gas, because if it was a gas, it would be poof, gone. So that's gone. Is it a liquid? It is a liquid. Yeah. Is it a solid? No, well, it can't be both a liquid and a solid. Is it an element? Can't tell. Is it a compound? Can't tell. Is it a mixture? Can't tell. Is it a solution? Can't tell. Is it a pure substance? Can't tell. Is it a homogeneous mixture? Can't tell because you don't even know if it's a mixture or a pure substance. Is it a heterogeneous mixture? Can't tell. All right, let's move on to the next view. So we know it's not a gas. We know it's a liquid. We know it's not a solid, and everything else is up for grabs. And we can't tell anything with the 1,000 times. Other than we're not seeing any parts. So I guess what we can conclude is that it's not a heterogeneous mixture. Right? If it was a heterogeneous mixture, we'd be seeing multiple different parts at this point. So I guess we can decide something. We know that it's not a heterogeneous mixture. Okay, let's move on to the next one. So we know it's not a gas. We know that it's a liquid. We know that it's not a solid. And we know that it's not a heterogeneous mixture. So let's have a look at this 10 million times view real closely. The first thing I see there is that there's more than one type of atom present, so it is not an element. The next thing I see is that there's different molecules present. So that means that it is not a compound and it is a mixture. Now, if it's not an element and it's not a compound, it can't be a pure substance, so that has to go. Now, is it a solution? Now, what a solution has is this. A solution has a major part, and that's called the solvent. And then a solution has a minor part, and that's called the solute. So when I look here, what I see is I see 1, 2, 3, 4, 5, 6, 7, 8, 9, about 10 of the larger molecules, not being too precise, but I see way more than 10 of the smaller molecules. So I'm going to say that this guy is a solution. You got one part that's much bigger abundance than the other. And then when we looked at it it's a mixture, right? So is it heterogeneous or homogeneous? Well, it was homogeneous because when we looked at it at the 1,000 times view, we didn't see, clearly distinct parts. So that was pretty complex, and you had to work through that slowly. You also needed to know that it was a solution, and a classic homogeneous mixture is a solution. Okay. Oh, these ones are kind of fun. Distinguishing chemical and physical change. So in a chemical change, atoms are reorganized in how they are connected. So when a chemical change occurs, there's a reorganization of what atoms are connected to what other atoms. In a physical change, no reorganization of how atoms are connected. Now, an important property of any change, whether it's physical or chemical, is that atoms are not transformed. So it is not possible to turn an atom of one type into an atom of another type. And the other thing is the number of atoms doesn't change. So the number of atoms doesn't change, right? So I'll show you what I mean. We have to decide if the change is impossible, a physical change, or a chemical change. So the first thing is we're going to start with a bunch of gray and white atoms. And because we can't transform one kind of atom into another kind of atom, we know that we can only end up with a bunch of gray and white atoms. So change number 2 here, where it looks like our white atoms got turned into green atoms, has to be impossible. It has to be impossible. So there it is. Now the other ones are kind of plausible at this point in time, but we need to think about the number of atoms of each type. So how many molecules do I have in my sample of X? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've got 12 molecules. And each molecule contains 2 times 2 white atoms and 2 gray atoms. So what does that mean? It means that we began with 24 whites and 24 grays, right? So to begin with, because 2 times 12 is 24, isn't it, right? So we started with 24 white and 24 grey. So for 1 and 3 to be possible, we've got to end up with 24 white and 24 grey. So in each case, we know that it's not a physical change because the atoms are reorganized how they're connected. So the only possibility is either impossible or chemical, right? So it's a 50-50. So impossible would be because we've messed up the number of atoms. So in change number 1, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 molecules. And each molecule has 4 whites and 2 greys. And so that would mean that I would have 48 whites and 24 greys. So that immediately tells me that I somehow magically gained another 24 white atoms. And that's just not possible. So that one has to be impossible. Okay, so we know that this is not a physical change because we've reorganized how the atoms are connected for number 3. So the question is it impossible or chemical? So in this case, I've got 4 molecules, and each molecule has 6 white atoms, and it has 6 grey. So 4 times 6, that's going to give me 24 whites. And 4 times 6 is going to give me 24 greys. So this one here, it is possible and it's a chemical change. So putting all of that together, we had 2 impossible and 1 chemical. All right, last objective. Let's see how we're going to go. Oh, this one's good. Distinguishing solid, liquid, and gas phases of a pure substance. So, if we have a graph here with temperature, this first temperature I'm going to put on here is what's called the melting point. And if I'm at a temperature lower than the melting point, I'll have a solid. And if I'm at a temperature greater than the melting point, I'll have a liquid. Then I'm going to mark a second temperature, and this one is called the boiling point. And if I am at temperatures that are greater than the boiling point, my substance will exist as a gas. And if I'm at temperatures lower than the boiling point, you guessed it, it'll be a liquid. So in solids, what I know is that the particles that make up my substance are close to one another and in an orderly arrangement. In liquids, my particles are close to one another, but they're kind of disorganized as to how they are arranged. And in gases, my particles are a long way away from each other. So what we have to do is to pick the diagram that corresponds to the substance at a particular temperature. So let's read this. It says there are 3 sets of sketches below showing the same pure molecular compound carbon monoxide that has the molecular formula CO. So this is made up of molecules that contain 1 carbon atom and 1 oxygen atom. So they are diatomic, heteroatomic molecules. Now you're going to go 3 sets of sketches at 3 different temperatures. Oh, I wonder what these could correspond to. The sketches are drawn as if a sample of carbon monoxide were under a microscope so powerful that individual atoms could be seen. Only 1 sketch in each set is correct. Use the slider to choose the correct sketch in each set. So the first thing is, whatever we get a picture of has to have molecules that contain 2 different atoms. If it doesn't have that, it's not the correct substance. All right? So you can't have molecules that contain two identical atoms. You can't have molecules that contain more than two atoms. And you can't have individual atoms. It has to be molecules that contain two atoms, and each atom has to be different. So that's the first thing. Now we've got to decide whether it is a solid, liquid, or gas. So the melting point of carbon monoxide is minus 205. So that means at temperatures lower than 205, we'll have a solid. The boiling point of carbon monoxide is minus 192. So that means at temperatures greater than 192, we're going to have a gas. So at minus 152, where are we? Well, we're out like here, aren't we? Minus 152 is definitely bigger than 192. So I put a gas in there, right? The particles are a long way away from each other, okay? All right, the next one is minus 210. So minus 210 is going to be there. So we're lower than the melting point. So we are in the solid area. So you can see I've got my carbon monoxide molecules close to one another and they're very organized. My next one is minus 197. So minus 197 is going to be like, I don't know, in here, right? It's less than 192, but it's greater than minus 205. So that's in the liquid area, right? So I've got my molecules close to one another, but they're kind of disorderly arranged, okay? And that's it. So that's how we do that. All right, so that concludes me working through one example of each of the objectives for this week, and I hope you found that helpful. Please let me know if you have any questions.